In this next example, we're going to be focusing on using areas to find integrals and knowing whether we should be using positive or negative values. So when you read the integral for part A, it says find the area under the curve, okay, integrate from negative 4 to negative 1. So we're going from negative 4 to negative 1. That would be A1. Part B is different. It's a different area. Part B is saying go from negative 1 to 4. Because this is below the x-axis, that is negative if we're going in the positive direction. So that would be negative A2. Okay. This time, for part C, we are going from 4 to negative 1. So I'd like you to put this answer. All right, let's clear that out. Okay, the next one. We're going from negative 4 all the way to positive 4. So this is positive, this is negative. So this would be equal to A1, the area here, minus A2, the area here. Okay, so we have negative 4 to positive 4, which is what we just had, A1 minus A2. That's a minus there. Minus 2 times, what is this? Negative 1 to 4. So that would be negative A2. So A1 minus A2 plus 2A2 ends up giving us A1 plus A2. Okay, in this example, we have the graph of the function f of x. It's composed of 3 line segments on a semicircle. So the first step is to find the equation of this line segment and use it to find the x-intercept of the line segment. So we can calculate the slope, negative 1 minus 3 over 5 minus 3. So it's a negative 2. Use any of the points, so y equals 3 minus 2 times the quantity x minus 3, point slope form. Do we simplify it? Sure, why not? I guess we'll put it in slope-intercept form. Might be easier to see. Y equals negative 2x plus 9. Find the y-intercept. X-intercept. We let y equal 0. So we get 9 halves is our x-intercept. All right. So we're going to be using that because we can now see that this is crossing right there at 4.5 or 9 halves. All right. Evaluate the integral from negative 7 all the way to 0. So we have some part under the x-axis and we have some part over the x-axis. So this is going to be equal to negative area of this triangle. So that would be what? 1/2 times 1, 2, 3. I can't see. I wrote all over it. 1, 2, 3, 4, 5 times a height of 1. So it'd be negative 5 halves. And then we need the positive area of this. So the area of a circle is pi times and the radius squared. But this is only a quarter circle. So it looks like that would be plus pi. All right, and our next part, we're going to evaluate the integral from 5 to 2. We're going this way. So anything under the x-axis is positive. Anything above is negative. So we have the area of this little tiny triangle right here. It's going to be positive 1/2. Base would be 0.5 times the height of 1. Okay, plus negative or minus 1/2, and this is 2.5 or 5 halves. And the height would be 3. I know I could leave it like that, but that would be 1/4 minus 15 fourths. Yeah, so that would give us negative 14/4 or -7/2. All right, so everything we've seen so far has been a continuous function, and continuity implies integrability. All right, so these functions are integrable because they are continuous. So if a function is continuous, it is integrable. If it is not integrable, then it's because it's not continuous. All right, so look at that. Do you remember this function, senior salta? Got a nice little jump function there. It's going from -1 up to +1. There's our function. And we're going to evaluate this integral by calculating the area above and below the curve. So we're going from -2 all the way to 3. So the area of this would be 2 times 1. The area of this would be 3 times 1. Okay, so this integral is going to be equal to -2 plus 3. That would be 1. Okay, so these next two problems are really good examples, especially to compare together. There's a lot of important information packed into this one statement. F is a continuous function and it's non-negative. Very important for an idea later. So we're going to approximate the integral from 0 to 3 using numeric methods as indicated by the data. What this is saying is we can use left hand, right hand, midpoint maybe, trapezoids. All right, so we're going to show that we're going to approximate this. We're going to approximate it by, and let's see, one thing that I've noticed is there are 1, 2, 3, 4, 5, 6 different pieces of information. Okay, so, well, 6 different rectangles we can use. So we can use left hand rectangles. We can use 6 right hand rectangles. And another thing that's pretty neat on this one, we have midpoints, right? We have midpoints. So we could also approximate this by using 3 midpoints. And I believe we could even do trapezoids. So we'll see if we feel like doing that later. All right, so back to this. To find the left-hand rectangles, we have, and another important thing to take note, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. All of those are 1/2. So we can pull out that 1/2. Left-hand heights will be 2. Oops, plus 4, plus 6, plus 7, plus 4, plus 1. All right, I believe that would be 12. This 1/2 times, we're going to use the right hand endpoints this time. Oops. So that means that we would have to start, instead of starting from 2, we're going to start from 4. Because we're taking the right side heights. Whoa. All right, so back to that, we get 4 plus 6 plus 7 plus 4 plus 1 plus 1. And if I added that up right, it's 12. And by 12, I meant 13.5. Oh, I thought that was the eraser. Okay. Now we have a midpoint. So 1/2 times, and we're going to use the midpoints of each of the rectangles. 4 plus 7 plus 1. Okay, so that would be 6. Yeah, that doesn't seem right, does it? And here's why. It's not 6 because they're not 1/2. If we're using the midpoint, we're actually going from 0 to 1, 1 to 2, and 2 to 3. So that would be 1. So that is 12. All right, so we could do trapezoidal, but again, I think we don't need to take the time to write that out right now. If you wanted to do it, wow, come on. All right, I'll write it out. So you have it. Trapezoidal, we could use 6. So we have 1/2 times the height in each case was 1/2. And we would have 2 plus 2 times 4 plus 2 times 6 plus 2 times 7 plus 2 times 4 plus 2 times 1 plus 5. And there we go. All right. So I'll answer these questions. Could any of these integral approximations represent approximations of the area? So that is yes, because f of x was non-negative. There's no parts under the x-axis that we would have to worry about. And then we have the last part here, approximate f prime of 1. Oh, we're going to approximate that. So we could use these two, we could use these two, we could use these two. Really, it doesn't matter because we're approximating. So I'm going to say 7 minus 6 over 1.5 minus 1. Show the difference quotient here, and that would be 2. Okay. This one I think we'll save for the next video.